Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes j, okay, that is adjacent to the node we just added into n prime. Okay. And inside each iteration in the inner for loop, what we do is this, the min operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So d to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. Okay. In the first iteration, so only the source is in the n prime. How many j's is connected to the source? Yeah, it's fully connected. Therefore, n minus 1 nodes, they will all be j, and we'll need to do min for each of these j. First iteration, we'll need to do n minus 1 comparison. Second iteration, how many? Because there's one more node being included into n prime, so number of j in the second iteration, only n minus 2. Third iteration, and we can go on until the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, the second step is not going to be called because there's no j remaining. So if we add all these together, this is the number of comparisons. N multiplying n minus 1 divided by 2. And this is in the scale of n squared. Big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale of n squared. That means the time complexity, the growing trend of the Dijkstra algorithm is this. When n approach when the network goes really big, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear. A straight line, sorry, the line is not very straight here. Now, there's an implementation available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. Right? So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So, nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good. There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Let me explain using an example. So we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. All traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking path DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again, right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see two possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C, also see two possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C would choose to go also clockwise to send traffic to A. Similarly, D sees also two paths. Okay. This direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, there's only one portion of the traffic. On link CD, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic begin to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So, given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CB is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, BC's this pass costs 0. This pass costs 2 plus E. B switch the other direction. CC's this pass, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. Okay. 1 on this link, 1 plus E on this link, and 2 plus E on this link, which is identical to 2 periods before. Okay. And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.